on enhancement type MOSFET. First, identify the region of operation. This is the symbol for enhancement type MOSFET. We will see the detailed symbols of MOSFET in detail. Gate terminal, drain terminal, and this is source terminal. Source terminal is grounded and gate terminal is kept at 1 volt, and for this MOSFET VT equal to 1.5 volt, and at drain 5 volt battery is connected. So we have to identify the region of operation for this MOSFET. This is the symbol for n channel MOSFET, and in this n channel MOSFET VT is given as 1.5 volt, VG is equal to 1 volt, VGS will be equal to VG minus VS will be equal to 1.1 volt minus 0 volt equal to 1 volt. So VGS equal to 0 volt. As we can see that VGS is less than VT, which is equal to 1.5 volt, VGS equal to 1 volt. As VGS is less than VT, we will say that this MOSFET is operating in cutoff region. This MOSFET is operating in cutoff region. Second, again identify the region of operation. Five volt is applied to the gate terminal and threshold voltage VT equal to 1 volt, and the source terminal is grounded. In this MOSFET we have to identify again the region of operation. We can see that Vs equal to 0 volt, Vg equal to 5 volt, so Vgs equal to Vg minus Vs will be equal to 5 minus 0 equal to 5 volt. Vt equal to 1 volt, so Vgs minus Vt will be equal to 5 minus 1 equal to 4 volt, and Vds equal to Vd minus Vs will be equal to 2 minus 0 equal to 2 volt. So we have calculated Vds, we have calculated Vgs minus Vt, and these two are sufficient. First we will check if Vgs is greater than equal to Vt. VGS equal to 5 volt, VT equal to 1 volt. As VGS is greater than VT, VGS is greater than VT, it is operating either in linear or in saturation region. It cannot be in cutoff. VDS, which is equal to 2 volt, is less than VGS minus VT, which is equal to 4 volt. So as it is VDS. If VDS is equal to 2 volt and it is less than VGS minus VT, so we can we will as we know that VDS is less than VGS minus VT, so this MOSFET will operate in linear region. Next case, identify the region of operation. VT equal to 1 volt. In this type of MOSFET, we know that VD equal to 5 volt, VG equal to 5 volt, VS equal to 0 volt. Sorry, this VG equal to 5 volt. Now VGS will be equal to VG minus VS, and this will be equal to 5 minus 0 equal to 5 volt. VDS, this voltage will be equal to VD minus VS will be equal to 5 minus 0 equal to 5 volt. Now VGS minus VT will be equal to 5 minus 1 will be equal to 4 volts. Now we can see that VDS is greater than VGS minus VT. VGS minus VT equal to 4 volt and VDS equal to 5 volt. As VDS is greater than VGS minus VT, therefore it is operating in saturation. So we will now keep in mind that whenever the gate and drain terminal are shorted, it will always operate in saturation. Next problem. For a MOSFET, for a MOSFET, gate and drain terminals are shorted. Gate and drain terminals are shorted. That is VDS equal to VGS, VT equal to 1 volt, and ID equal to 1 milliamperes for VGS equal to 2 volt. Then for VGS equal to 3 volt, ID equal to what? This question was asked in GATE 2004 in electronics engineering. We know that if gate and drain terminals are shorted, it will operate in saturation. As we have already seen, if gate and drain terminals are shorted, it will always operate in saturation. If it is operating in saturation, drain current ID is equal to 1 by 2 into mu1 into C oxide into W by L into VGS minus VT whole square. This will be a constant, so ID is directly proportional to VGS minus VT whole square. ID1 will be directly proportional to VGS1 minus VT whole square. ID2 will be directly proportional to VGS2 minus VT whole square. So we will have this equation: ID1 upon ID2 will be equal to VGS1 minus VT whole square divided by VGS2 minus VT whole square. ID1 is given 1 milliampere divided by ID2 will be equal to VGS1 is equal to 2 volt. So 2 minus 1 VT equal to 1 whole square divided by 3 minus 1 whole square will be equal to 1 by 4. So ID2 will be equal to 4 milliamperes. Now next question. The drain current of MOSFET ID is equal to K into VGS minus VT whole square, where K is constant. Then the magnitude of transconductance GM will be equal to what? This question was asked in GATE 2008 in electronics engineering. We have to calculate transconductance GM. We know that transconductance GM is equal to del ID upon del VGS when VDS equal to constant. VDS equal to constant. So now we can calculate this transconductance GM as del by del VGS into K into VGS minus VT whole square. Differentiating this, we get twice K into VGS minus VT. So this would be the transconductance of a MOSFET when it is operating in saturation. Now we will see the symbols, circuit symbols for enhancement type MOSFET and depletion type MOSFET. First we will see for depletion type MOSFET. Circuit symbols for depletion type of MOSFET. And depletion type MOSFET, we will have these symbols. This is body terminal, this is source terminal, this is drain terminal, and this is gate terminal. If this symbol is used, it is of n channel MOSFET. For p channel depletion type MOSFET, the arrow will be in outward direction. This is to source, this is body, this is drain, and this is gate. This is for p channel enhancement type MOSFET. These are the circuit symbols for depletion type MOSFET. This is p channel depletion MOSFET. Now enhancement MOSFET. For enhancement type MOSFET, we will have three different symbols. First will be like depletion MOSFET. This line will be dotted, gate terminal, drain terminal, and this is source terminal. And we will have one more terminal, that is body. For p channel, the symbol will be again like depletion type MOSFET. The arrow will be outward. Body, drain, gate, and this is source terminal. We will use one more symbol for simplicity. This is the symbol for n channel MOSFET. The arrow will be outward on the source terminal, and if the arrow is into the MOSFET, this is p channel MOSFET. And we will have one more symbol for n channel MOSFET. Simple, if this symbol is used, it will be considered as n channel MOSFET. And if we put a bubble on the gate terminal, this would be the symbol for p channel MOSFET. These are n channel MOSFETs, enhancement MOSFET, and these are p channel enhancement type MOSFETs. Now we will see the body effect in MOSFETs. If this is MOSFET and this is body terminal kept at ground, so VB equal to 0 volt. This is source terminal, and at this source terminal, if we have applied a voltage Vs, if during operation, if we have VSB, source to body voltage, source is n type material and this is p type substrate. So if VSB is greater than 0, then there will be a reverse biasing between at this junction n and p. At this junction there will be a reverse biasing, and due to this reverse biasing, the depletion layer will penetrate more into the region. If we further increase VSB, there will be more penetration of depletion region into this region. If this depletion layer width is large in this region, then it becomes more difficult to remove this depletion layer and form a channel between source and drain terminal. So we will say that if we have applied a source to body voltage which is greater than 0, threshold voltage Vt of the device increases. So if VSB is greater than 0, threshold voltage of the device increases. And we can decrease this threshold voltage by using a material that is P plus polycrystalline silicon instead of a metal. If P plus polycrystalline silicon is used, then threshold voltage Vt can be decreased. So uh, the device can be enabled at lower voltages of applied VGS. So it will be advantage. So nowadays in modern MOSFETs, instead of metal, we use only P-type polycrystalline silicon. So this was all about enhancement type MOSFET and depletion type MOSFET.